Okay, people at home, somebody give me a yes, I can hear you.
Yes, I can hear you.
Okay, great. All right, so I've started to give back exams, but we're gonna have to pause that in order to get going here. And you can pick up your exam by coming to lecture. If you haven't got it yet, you can come up afterwards. You can pick it up during lab, or you can pick it up during office hours. So today we're going to extend what we have done so far with exploitation models. And remember, we have a very, very basic exploitation model that is kind of stupid on the surface, but that actually tells us some things that we need to know about nature and gives us a way to model them so that we could maybe understand and even possibly predict what's going to happen in nature. So that arises from these two guys, Lotka and Volterra, who decided that they would simply try to understand predators and prey in terms of their births and deaths. They made some really bad assumptions that seemed to work out for us, though. They assumed that the prey don't compete with each other, and they assume that every prey dies because it was eaten by a predator. And what that allows us to do is convert this growth rate, being births minus deaths, into something that specifies how many individuals are born and how many die. So if the prey don't compete with each other, then dNdt for the prey is simply R times N. It's exponential growth. There's nothing to check the prey except the predators. So that's down here. B is actually exponential growth, R times N. The death rate, making the assumption that everybody dies because they're eaten then, also allows us to specify how that happens. So the rate at which animals die in the population, that is the death rate of the population, depends on the number of organisms in the population times the number of predators there are that can eat them, times this little p, which is the rate at which one predator catches one prey. So this is the predation rate. All right, so this represents the deaths, this represents the births. For the predator population, they made similar, really dumbass assumptions that also seem to work for us. They just assumed that the birth rate of the predators depends on how many prey they can eat and nothing else. They decided that the death rate is just the death rate, whatever it is. And they made absolutely no commitments about what would cause the death of the predator. It's just they live for so long and then they just keel over for no reason. Who knows? But what that does is allow us to then convert this births minus deaths into a very simple model. And the birth rate is going to be the rate at which prey are eaten, which is P times N times P from the previous equation, times this little factor A, which is the rate at which one prey is converted into one baby predator. Okay, so as I said, if you need 10 prey to store up enough energy to reproduce one baby, then it's 0.1. If it's 100 prey required to store up enough energy, then it's 0.01. Okay, but these are real numbers. Not that we are going to work with these real numbers, but just so you know. And then they said that the death rate, okay, that's just kind of random. There's going to be some death rate, which is they're going to call D, and that's the rate at which predators die. And here's the number of predators dying that are available to die. So with absolutely no biology in the death rate of the predators, here's our equation. This is the birth rate is the number of prey that get caught times the rate at which prey are converted into predator minus the death rate of the predators times the number of predators. Okay, so really very, very simple equations. And what that does is allow us to calculate what the isocline should be. And the isoclines, where these numbers equals 0, or births equal deaths, are found at constant values, which is crazy. Okay, the constant value of the prey isocline is actually found by solving this equation. Okay, and n cancels out here, so you're left with r equals p times the number of predators. And so the prey reach 0 growth when the number of predators equals this constant, which is, totally strange. But that's what it looks like. Okay, and here is r divided by p. This is the intercept. Now, right here, it's on the y-axis, but it's possible for the intercept to be down here on the x-axis, as you will see later on in this lecture. That's when maybe there is more than one predator. So the end point of the prey isocline is always r divided by p, regardless of where it falls. Okay, and this is the dynamics of the prey. They increase when the number of predators is below that r divided by p number, and they decrease when it's greater. There are too many predators here eating the prey for the population to grow. Here, there are not enough predators to check the exponential growth of the prey. So, do the same thing for the predators, and again, we set births equal to deaths, so that's AP NP equals DP right here. And we can cancel P, both sides, and then we have AP times N equals D. And then the number of prey then would equal D divided by AP. Again, that's a constant. The predator population reaches 0 growth when the number of prey is exactly this constant. If the number of prey is below that, then the predators don't have enough food and they decline. Some of them die. If the number of prey is above this, then they increase. Okay, and once again, it seems like this should be completely useless to us because it's so counterintuitive. But this is what it looks like when you graph it. Here's the intercept of the predator isocline. It is always D divided by AP. Okay, and once again, I've got it on the x-axis here because it's strictly related to the number of prey. But it could actually be anywhere here. It could be on the y-axis if the predator has another prey. So the predator could have a growing population, even though there is 0 prey, if it's got another prey to eat. And you'll see how we work that in later. That's some of the modifications we're going to do today. Okay, but this is the dynamics. So here's your constant level of prey. If you have more prey than that, then there's enough food for the predators to reproduce. If there are fewer prey than that, then the predators have to decline. So once again, really looking like a dumbass model. If we put them on the same graph, this is what we get, though. We get an equilibrium. Oh, that's good, because we know that predators and prey can coexist at equilibrium. Now, this happens to be an unstable equilibrium, because if you move off of it, the point has no way of going back. So the combination of predators and prey right here will simply cycle around, and it won't ever go back to the equilibrium. It's not an unstable equilibrium in the same sense that the competition equilibrium was unstable, because in that case, one of the other species went extinct. Here, they don't go extinct, but they also don't go back to that stable combination of numbers. So it's an unstable equilibrium. The other thing you can get, though, is the cycling. And we know that cycling is an important feature of many predator-prey systems, and it happens in a particular way. The prey always lead. The predator always lags. So here, the prey will reach their minimum at a time when the predators are still decreasing. The predators will reach their minimum after the prey have started to increase again. When the prey reach their maximum, the predators are still increasing and won't reach their maximum until later. So this set of oscillations here exactly matches the predator-prey system of the lynx and snowshoe hare. And so that's a very important result. So we have a couple of very important results. Now, clearly, this is really approximate. And people looked at this for a very long time. They looked at it for 40 years, really, and said, yeah, we can do certain things with this, but this is not really the most useful thing because we know that predator-prey systems are more complicated than that. So this was an oddity that was used in the classroom to illustrate how things could work. But it wasn't really applied in nature all that often because so many systems didn't fit it. So in the 1960s, people started looking more closely at this and started saying, well, Lotka and Volterra made these assumptions. What happens if we relax the assumptions? What would happen? Would we get a more realistic predator-prey model? And so Robert Macarthur, whose name you've already heard, he was the guy who did his doctoral dissertation on the 5 species of warblers that demonstrated ecological segregation. He got a job at Princeton and took on a student named Mike Rosenzweig. And so they sat around drinking coffee a lot and playing with this idea. And they got the idea, well, what would this graph look like if we allowed density dependence to occur in the prey? So if we let the prey compete with each other, how would that change what this system of isoclines looks like? Well, this is how it would change. Because what you see here on the left is the basic Lotka Volterra model, and on the right is what Macarthur and Rosenzweig postulated would happen if you allowed the prey to compete. So now you have density-dependent growth. And you have the possibility of zero growth of the prey when they reach their carrying capacity. And so this sloping line here, this humped curve, is now exactly the same curve as we had when we graphed dn/dt versus n. That's why I showed you that graph. Okay, it starts out low here. It rises to a peak, and then it goes to 0. Now, we're going to interpret it slightly differently in the context of a predator-prey system. We're going to ask, how many predators does it take to stop the growth of the prey population? Well, we know that at small prey population sizes, way over here, there's not much reproduction going on simply because there are just not that many individuals. N is a small number, so you're getting a small change in the prey population per unit time. It only takes a few predators down here to eat enough prey to stop the population from growing. So we're framing our discussion of this curve a little differently. When there's lots of individuals in the prey population, and when there are plenty of resources to go around, then they're growing at a very high rate. And it will take lots of predators to check the growth of the prey population and cause it to stop growing. If you're growing at a rate of 10% a year, you have to have enough predators to eat 10% of the population every single year. So you're going to have a lot of predators here to cause the prey population to stop growing. And so this number here on the predator axis is much larger than this number here. Well, okay, that makes a lot of sense, doesn't it? If you have more prey reproduction, you need more predators to stop the population from growing. Of course, as competition among the prey increases as their population increases, their rate of growth starts to decline because the rate of reproduction is now being limited by competition. So you need progressively fewer predators to cause the prey population to stop growing. You need fewer predators here because the prey are competing very intensely with one another. And so they have a lower reproductive rate to begin with. And you don't need as many predators to stop them from growing as you did here. And of course, if the prey reach their carrying capacity, what's dNdt? It's 0. So how many predators do you need to stop the prey population from growing if they've reached their carrying capacity? 0. So that's why this curve looks like this. This relates the number of predators required to check the growth of the prey population to the size of that population. Okay, at K, the prey population isn't growing anyway. You need 0 predators. So you intersect this axis at predators equals 0. Up here, you need a whole bunch of predators because the prey population is reproducing really, really rapidly. Now, you need to make the mental jump here. We've changed the shape of the prey isocline from a straight line to this curve, but the behavior of the populations has not changed. We still get exactly the same cycling. It's just that the shape of the areas on the graph in which the points are moving in a particular direction has changed. This is going to be very important. You're going to have to be able to track this. Okay, so over here, you are below the prey isocline. That means that the prey population can increase because there aren't enough predators. Okay, but you're below the predator isocline. Actually, you're below the predator isocline too. So there are not enough prey to support the predator population. So predators decline and prey increase. So the point moves this way. This is exactly what it did when the lines were straight. When you cross the predator isocline, suddenly there are enough prey for the predator population to grow, so it starts moving up. And as long as you are below this curve here, the prey population can continue to grow. Once you hit that curve, though, the prey population has to start to decrease. However, you're still on the right side of the predator isocline, so the predators continue to increase. So prey decrease, predators increase, your net movement is that away. You still get the cycling. This is exactly the same result as we got when the lines were straight. But notice something about this graph that is not true of the Lotka Volterra graph. We've got the predators intersecting the prey at the peak of the prey curve. And if we had moved the predator isocline to the left or right on the Lotka Volterra graph, it would have made absolutely no difference. But it makes a big difference now. It's going to change things dramatically if we move this predator isocline to the right or to the left. So here are the three cases that arise from allowing prey to compete with one another in the Macarthur-Rosenzweig formulation of the model. So what happens here? Well, in every case, this quadrant right here, you move down and to the right. In this one, you move up and to the right, up and to the left, down and to the left. But the results are quite different. If the intersection is to the left of this hump, look what happens. You move down and to the right till you cross the isocline. Then you move up and to the right till you cross this isocline. Then you move up and to the left. And then what happens? You never cross another isocline. You go back down to the left. There's nothing to stop this movement of the two populations. The predator is on the wrong side of its isocline, so they're decreasing. The prey are above their isocline, so they're decreasing. And there's nothing to stop them. What's the result? The predators drive the prey extinct. We couldn't get that from Lotka Volterra. This is, once Macarthur and Rosenzweig realized this, they understood how big an improvement this was. If the cycling is right around the peak in the prey isocline, you're going to get that same case as Lotka Volterra. You get an unstable equilibrium, but stable cycling. Okay, now it is possible for the oscillations to be so wide that you could do this, but we think of this as the equivalent of the Lotka Volterra formulation pretty much, because in most cases, you will eventually hit this isocline and turn. Okay, if the intersection is to the right of the hump, look what happens. In this section of the graph, a combination of predators and prey will change down and to the right because the prey can increase, but the predators must decrease. So it goes that way. When it hits the predator isocline, it turns up and to the right, because now the predators have enough prey to live and reproduce, and the prey are still able to increase until they hit their isocline. Once they cross their isocline, again, they go up and to the left, because now the prey cannot continue to increase. There are too many predators. But then they hit this isocline and they turn, and then they hit this isocline and they turn again. Basically, if you have an intersection on the right-hand side of the hump, you spiral back into this equilibrium, regardless of where you start, as long as it's, you know, the real world and not some strange universe where you have tremendous changes in the numbers. But for reasonable changes in the numbers, an intersection on the right of the hump gives you stable coexistence. It doesn't just give you an equilibrium. Lotka Volterra models give you an equilibrium, but it's not stable. This is a stable equilibrium. Now, what was it we were trying to explain in nature? We were trying to explain stable coexistence, cycling, and extinction. And we have all of those now. We also have this unstable equilibrium here. That's a really interesting case. Okay, so the Macarthur-Rosenzweig change, which is simply to let the prey compete with one another, brought us almost all the way to the reality of nature. We can model almost anything using this very simple graphical model. And we can take a point that represents a combination of predators and prey, and by knowing where the predator isocline intersects the prey isocline, We can make predictions about what's going to happen to a predator-prey system. That's huge. That's a huge advance. So we know almost everything that there is to know about nature. But there was one other thing that we saw last time that we haven't got on here, right? And that was the idea that prey can have a refuge that can prevent the predators from driving them extinct. And normally, if you have this kind of situation here, where the predator is very efficient and intersects the prey isocline on the left side, it's going to drive those prey extinct. But we know from Huffaker's mite experiment that prey can have a refuge. And if the predators can't get them below a certain number, they can always bounce back, even if you have this situation. So what would that be like in nature? Well, we had Huffaker's experiment in the lab. What about a natural analogy that might make this more real to us? Well, okay, so think about possums foraging for little invertebrates on the forest floor, which is kind of what they do. Okay, so if a possum sees a little beetle out in the open, it's going to eat it. And possums eat a lot of beetles. Okay, so there's a possibility that an interaction between a possum and beetles might look like this. But what if a certain number of beetles could crawl under a log where the possum can't get them? Well, then you'd always have some beetles being protected from the possum. And it would be impossible then for the possum to actually cause them to go extinct, because there would be some number of prey here that would cause this decrease to turn back. So what might that look like? Well, we could try to write it in the equation. Even ecologists aren't that ambitious. We don't want to do stuff like that because it's too hard. Let's just try to make just pull it out of thin air and put something on the graph that would make it turn. Well, there you go. That's what it looks like. This is how we envision a prey refuge. Basically, you have the prey competing. Okay, so it's density-dependent growth of the prey, but at some number down here, the prey are no longer vulnerable to the predator. The beetles at this number right here can all hide under a log. And so the predator can't get them anymore. So this changes then the trajectory of this interaction. Normally, we'd expect this to be a situation in which predators cause prey extinction. So in this area here, you're moving down and to the right. Here you're moving up and to the right. Here you're moving up and to the left. And here you're moving down and to the left. And we would normally expect the extinction of the prey. But when you hit this isocline, you move into a space where you're moving back that way. So basically, you start out looking like the prey is going to go extinct. It's headed for that axis, but as soon as it crosses this, it goes back. Gets in here, well, now it's forced that way. Back, back, and now the cycle starts over again. So basically, we're envisioning a prey refuge as something that interrupts the decline of the prey and causes the trajectory of a predator-prey system to sort of walk down this thing here. And here's what it looks like. The kink in the prey isocline prevents the prey from going extinct, even if it's an unstable interaction. Okay, so we're not trying to do anything really complicated mathematically here because we don't like complicated math. We're just saying, okay, what can we slap on this graph to illustrate what a refuge would look like? And in fact, people have used this method graphically in scientific papers, not very often, but occasionally, to model a situation in which there's a predator and a prey, and there's a prey refuge. And they've actually established what this minimum density here is that allows the prey to escape predation. But basically, you do what you might expect here. You circle around like this, and then you hit this axis. Whoop, hit this isocline. Yeah, where's my cursor? Hit this isocline and go back. Hit this isocline, go back, and then start over. Back. Just sort of wobbling down this isocline back and forth, preventing the extinction of the prey. So with this modification, we've modified the prey isocline twice now. We've allowed them to compete, and we've put in a minimum density below which they are invulnerable to predators. We now have everything that occurs in nature. We have stable coexistence. We have cycling. We have extinction. And we have refuges that allow the prey to escape extinction. That was everything on our checklist. And we did it with two modifications of the prey isocline. So what you need to do then is to keep track. You need to track the changes in the shapes of these areas. Notice that there's still 1, 2, 3, and 4 areas on this graph that are divided by these isoclines. They are exactly the same areas as in the simple Lotka Volterra graph, but they have different shapes. So I'm posting a whole bunch of these for you to practice on, just to make sure you can draw the arrows and recognize what happens when you have a graph that shows you a refuge. What happens when you see a graph where the prey are competing. So you need to be able to identify those things. You need to be able to track the trajectory of the combination of predators and prey. So they're getting posted later today. So we've modified the prey isocline twice. You're saying, well, we haven't paid any attention to the predators. Are the predators worth ignoring? Well, let's examine that predator isocline. So what we are saying here with this straight up and down predator isocline is there is a density of prey that allows the predator population to grow. And it's independent of the number of predators. If you have 10 predators, this graph would suggest you need the same number of prey as if you had 10,000 predators. Well, that's kind of stupid. You know that that's not true. Larger predator populations should require more prey. So that thing should not be straight up and down. It should not be a constant. If you have this number of predators here, you might need a relatively low number of prey. But if you have this number of predators, you should need way more prey. This line shouldn't be straight up and down. It should slope. It should look something like that. Okay, so in looking at the Macarthur Rosenzweig graphs that we just saw, there is a density of prey. So that is a density-dependent predator. There's always a density of prey that allows it to increase. When the line slopes like this, it's not a density, because look, for this number of predators, you need that many prey. For this number of predators, you need that many prey. It's a ratio. There's a ratio of predators to prey that is required for the predator population to grow. So this is what we call a ratio-dependent predator. A density-dependent predator will have an isocline that's straight up and down. But a ratio-dependent predator will require more prey for bigger predator populations, and it'll slope like this. So this is a typical model of a ratio-dependent predator and a prey that exhibits density dependence. Look at where the intersection is right here. What can we say about that intersection point? It's to the right of the hump. It's stable. Ratio-dependent predators are involved in stable predator-prey interactions. They typically are stable. Density-dependent predators, and there are density-dependent predators. There are systems that behave in a density-dependent way. They can have either stability or cycling or extinction. Ratio-dependent predators, not so much. They're virtually all stable. Okay, so this end of the prey isocline would be R divided by P. This end of the predator isocline would be D divided by AP. That's the intersections, right? That's the axis intercepts. And this one over here for the prey is always going to be K. This is the predator. This is the prey. So you need to remember who's who, what these intercepts mean. And then you have to remember again that the shapes of the spaces on this graph have changed, but the behaviors are very predictable. In this section here, you are to the left of the predator isocline. There are not enough prey in this area here. So everywhere here, the predator decreases, the predator decreases. But in this little section here, the predator is decreasing, but the prey can increase. So the net movement is this way. When you cross the predator isocline, there are now enough prey for the predator to grow. The prey are still under their isocline, so you switch from going down and to the right to going up and to the right. When you cross the prey isocline, now the prey have to decrease. But you're still in this area here where there are enough prey for the predator, so you go down and to the right first, up and to the right, up and to the left. And now in this section, both species are declining this way, this way, this. And you spiral in to stability. The shapes have changed, but the behavior of the predator and prey populations has not. You need to be able to mentally make that transfer. Now, we get some interesting things when we allow the predator isocline to change, when we relax the assumptions of density dependent and make it more ratio dependent. Notice that this one hits the y-axis. That means that there are enough prey here for the predator to increase. The predator can increase in this little segment, even though the number of prey could be 0. How's that possible? They have more than one prey. This is a switching predator. It has more than one prey. And so it's perfectly possible for a predator to have positive population growth, even when one of its prey is absent. Now, there's something that interesting about this, and you have to sort of notice it. How many areas of the graph are there now? Well, we've got our 4. Got 1, 2, 3, 4. We have a fifth area here. So you have to figure out, okay, this is an extra thing that we didn't have before. How will the two populations behave here? Well, okay, it's to the right of the predator isocline, so predators can increase. But it's above the prey isocline, so prey must decrease. In this little wedge here, the predators do drive the prey extinct. And of course, if you have a combination of points way out here, then the predators will have to decrease and the prey will decrease, and you'll again get extinction. Mostly we pay attention to areas close to these equilibria though. The other thing about this is you have two equilibria. This is our gold standard stable equilibrium, but this one, look what happens if you move away. If you go into this direction, both populations decline. Oops, lost my cursor. If you go up here, both populations decline. The prey go extinct. If you move away from this equilibrium here, the predators increase, the prey decrease, the prey go extinct. You didn't go back to the equilibrium. It's an unstable equilibrium. You're never going back if you move away from it. If you move away from this equilibrium into this space, the prey increase, but you're above the predator isocline and they have to decrease. So here, if you go into this region, if you push the number of predators and prey here, it's going to do this. But when it crosses the predator isocline, it'll change direction. You push it over here, it'll do this, 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 and so it'll spiral into the stable coexistence. So if you move away here, the prey go extinct. If you move away here, you move from the unstable equilibrium to the stable one. I think you can see that we can get some pretty complicated interactions modeled here. These are not just imaginary. We have seen examples of every one of the things I'm going to show you actually in nature. We've seen, especially when we introduce a new species to an environment, or when we change the environment to favor either a predator or its prey. Think about wolves and deer. People like to hunt deer. People don't like wolves. So we manipulate the environment to change the number of deer for our purposes. But if we have an unstable equilibrium between wolves and deer, we may unintentionally cause the extinction of the deer. These kinds of interactions are way more common than you might expect. And again, blaming the British just as I blame them for rabbits and cactus and cactoblastis moths in Australia. They introduced bass into Lake Victoria in Africa, caused the extinction of some 300 out of 500 native cichlid species. Good intentions often have bad side effects because of this very thing, this kind of really interesting, complex interaction where there are stable and unstable points. Okay, so we have then ratio-dependent predators. Here's another way that the predator isocline can change. So we made two alterations possible for the prey. Here's a second alteration of the predator. What's going on here? Well, look, above a certain point, no increase in the number of prey changes the number of predators. It reaches a constant. It doesn't matter how many prey there are. The predator doesn't change. Why is that? The predator is saturated with prey. It literally cannot eat any more than it's already eating. And it's limited by something else. Whenever you see the predator isocline do something like this, the predator reaches a point where it's not limited by the prey anymore. It's limited by something else. Really terrific example is songbirds that nest in the spring that eat insects. When insect abundance increases, so does the number of nesting pairs, because the environment can support more. But at some point, the number of insects becomes irrelevant, and the number of nesting pairs doesn't change anymore because the nest sites have become limiting. Although there's plenty of food out there, there's not enough places to make a nest. So the number of insects in the environment, which is out here, becomes totally irrelevant. The predator is limited by nest sites, not by insects. Okay. So here you have kind of a real steep ratio dependence and predator saturation. You can have a much shallower slope here. You can have real obvious ratio dependence and saturation, or you could have a density dependent predator where the line goes straight up for a while and then turns. Okay, so here's a very clearly ratio dependent predator that becomes saturated by prey and is limited by something else. And once again, look at what we got here. Stable equilibrium. Okay, there are many ways to get a stable equilibrium. And that's why predators don't drive their prey extinct very often. They can in some cases, but in many cases, we know that the way that they interact promotes stability. Okay, so you can get all kinds of crazy, complicated graphs here. I'm going to give you some examples to work on that are way more complicated than I'd ever give you on an exam, just so you can have the experience of puzzling out which way those stupid arrows are supposed to go. Okay, so this is a ratio-dependent predator with an alternative prey. There's no prey refuge on here. That would be something I'd expect you to be able to say about this. If I were to ask you to describe these characteristics, you'd have to say something like that. Here's a ratio-dependent predator. See, the line is not straight up and down. So it's sloping, so it's ratio-dependent, and it saturates. And here's a density-dependent growth of the prey, and the prey has a refuge. Oh my, that's really complicated. There are lots of places on this graph. You have your standard for this way, this way, this way, and this way. But now you have this one and this one in addition. And look, you have 1, 2, 3 equilibria. Oh dear. Okay, so there's a limit to the kinds of things I will ask you on exams, but I will give you examples of these more complicated things so that you get the practice of figuring out where the combination of predators and prey will go over time. Over here, it's always the same. It's always down and to the right, up to the right, up to the left, down to the left. This is more interesting. Notice that this over here is basically the same situation as here. You're above the prey isocline. You're to the right of the predator, so you go up and you go, the prey go down, so you move in that direction. And basically, this is a stable equilibrium. Unstable, stable. So there's lots and lots of ways that we could pose these questions. I'm certainly not going to pose extremely complicated ones on the exam, because I want you to be able to do something else on the exam. However, do take these graphs seriously when I get them posted, because they will help you immensely. Okay, here's an example of how the lines go. So here's our stable equilibrium over here. Here's Here's the way the lines go. They go right back to here. This one is unstable because if you go here, you go that way. If you go here, you go that way. Here, you go away from it. Here, you go away from it. But then this one's stable. So you just have to think it through. You've always got your basic 4 areas on the model, and that's what this is. But you've then got these 2 extra areas. You have to think through how a combination of predators and prey might change over time in those extra areas. Okay, so we can model virtually any predator-prey system we find in nature using these basic tenets. We have the basic Lotka Volterra model, which is the straight lines. We can modify the prey in 2 ways. We can give them a refuge, and we can make them compete with each other, show density-dependent growth. We can have the predators altered in 2 ways. We can make them ratio-dependent, and we can cause them to saturate and be limited to something else, by something else. Either way, we have all the tools we need to model these interactions in nature. And this has been tremendously successful for us. These basic graphical models have found wide application. Notice that they often don't talk about specific numbers. They talk about trends, like the prey will decrease or the predators will increase. Oftentimes, that's more important to us than making a prediction of actual numbers. But that's the way this goes. So if we have questions, let's take them now, either in class or at home. All right, I have the exams. If you want to come up and get your exam, if I haven't given it back to you, please do. You can claim your exam in lecture, you can claim your exam in lab, or you can come by during office hours to claim it. All right, I am going to stop sharing now, and I'm gonna log out. I will see you all in lab if you're coming. Please bring your lab reports from the community very soon. We want to get those in.